Good afternoon, everybody. If you're not at the Energising the UK Battery Supply Chain Part 8 Battery Recycling meeting, you're in the wrong meeting. So, but since most of the names I recognise. So good afternoon and welcome. As I said, this is Part 8. The SCI has been running this series of workshops for just over 2 years. In an attempt to get people to understand that the chemicals that go into batteries are just as important as everything else. In fact, it doesn't work without the chemistry, but never mind. So at the last meeting, which was about anodes and other materials, there was a big cry from the participants to revisit battery recycling. We looked at it in episode 3 a long time ago because a lot of things have happened. So can I go to the next slide? So I'll just give you a quick introduction to everybody. We then have Anwar Sattar from WMG, who is the principal author of a very wonderful report on battery recycling, which you should all download and read. We'll then move on to Sarah from Benchmark, who is going to be talking about how you balance out the numbers and things like that. So I think that's really quite important. There's all sorts of reasons why we should understand those, and we need to get to it. And then lastly, we're going to have Roger Morton from EMR, who's a long-time participant in these workshops, talking about how you would build not just a commercially viable circular economy, but also a safe one, because we're dealing with some interesting chemicals and they come in various sizes and shapes. So for those of you who haven't been here before, we have these 3 shortish introductory talks. There will be a time for a little bit of questions, probably after the 3 of them, but then we'll go into breakout discussions. There are 3 groups. You get to be in a small group and you get to talk about what you've learned, what's interesting, what you would also like to hear, because as I say, we've been running these for a couple of years, and usually the subsequent meetings are actually decided by the participants in the previous meetings. So that will be useful. If you could set your name, as it says, to your name and the organization, that means that when you get put into the breakout rooms, the system knows what to do and things like that. So here are our 3 speakers. As I say, first will be Anwar, and then Sarah, and then Roger. So they all are very, very knowledgeable about this area. They've all been involved in it for a long time. So without too much further ado, if I could hand over to Anwar, would you like to give your presentation, please?
Okay, can you guys see that?
Yes.
Okay, good. So hi everyone, my name is Anwar Sattar. I'm the principal engineer at WMG in battery recycling, and I lead the battery recycling activities here at WMG. So today my presentation is developing a battery recycling industry in the UK. I hope you enjoy, and hopefully you have plenty of questions to ask. So firstly, I'd just like to share this slide quite quickly. There's a number of different types of electric vehicles that are being sold, so or electrified vehicles, should I say. The most important thing when it comes to battery recycling is the battery chemistry and the battery mass. Now, I won't spend too much time on this because I'm going to run over, but essentially you can see that the chemistry ranges from LFP, which is the lithium iron phosphate. It doesn't really have that much value when it comes to recycling, although we're trying to change that at WMG. To this NMC and NCA, which is the nickel manganese cobalt and the nickel cobalt aluminium, and these have quite a high value. Now, they can be anything from less than 10 kgs to over 1,000 kilograms, as in the case of some of the newer battery packs that are coming out in America. I think the biggest one is something like 1,300 kgs that I've seen so far, and that's in the new EV Hummer, if you want to have a look at it. So how is the electric revolution progressing? Well, actually pretty well. So if we look at the numbers from the SMMT, although the vehicle industry in the UK is not doing that well at the moment, more than 50% of the vehicles that are being sold contain some form of traction battery. And obviously these batteries are then going to come to the end of life and require recycling. There's also the updated legislations from the EU. So this is a big driver for battery recycling. So at the moment, the recycling efficiency, so a recycler must be able to recycle 50% of the battery by mass. Now, what that means is 50% of the battery must be converted into a sellable product before it can be considered recycling. That's quite a stringent criteria. But in 2025, or at the end of 2025, beginning of 2026, it's going to increase to 65%. And there's also going to be an introduction of recycling targets for certain metals. So 90% for the cobalt, the nickel, and the copper, and 35% for the lithium. And then in 2030, that recycling target is going to increase to 70%, and 95% recycling targets for the cobalt, nickel, and copper, and 70% for the lithium. More interestingly, however, is that in 2030, they're going to introduce a new concept, which is you have to have a recycled content of material per every cell that's made. And so it's 12% for cobalt, 4% for lithium and nickel. And then in 2035, that increases. And you can see there what it increases to. So the lithium-ion battery supply chain, well, essentially this is what it looks like. So you've got the mining, which is done by the miners. You get a variety of different materials, which are then refined to make, I guess, refined materials. And then these are then made into the battery chemicals. And then they go into the cell, and then finally into a pack. And then when it comes to recycling, essentially, most of the recycling comes back to this refining part. However, there is some possibility of also getting it back to the cathode material, anode material. So the sort of the products that, or the active chemicals that go into a battery, there's also a possibility to recycle it back into that as well. Of course, the battery recycling, the batteries material supply chain is a global industry, it's a global supply chain. So if we look at lithium, for example, it's mined mainly in Australia or Chile, but then it's almost all of it is refined in China. And then the electrochemical active materials are also refined in China as well, before it gets sent off to other places for the eventually putting it into batteries. And of course, what this means is that in the UK, we've got thousands of tons of these materials coming in. So we've got lithium, cobalt, nickel, graphite, etc. And obviously, we want to retain those as much as we can. And so battery recycling is, of course, enabling us to do that and retain it here in the UK rather than shipping it off abroad, only to then buy it back so that we can put it into the cars that we make here. A lithium-ion battery essentially can come in many shapes and forms. So you've got cylindrical cells, you've got pouch cells, you've got prismatic cells, but essentially, once you look underneath, they're almost all the same. You've got an anode, which is the graphite and copper, and you've got a cathode, which is aluminium, and then you have the coating, which is a lithium transition metal oxide. And then essentially you've got separators in the middle. And the way it works is you've got lithium travels from the anode to the cathode and vice versa when you're charging and discharging. And then this chart here shows the sort of the material composition of a battery or lithium-ion cell. The battery recycling process itself is a three-stage process. So essentially, you've got your batteries. The first stage is the shredding and sorting, and then that sorts it into different fractions. But the most valuable component is called the black mass. The black mass then goes into a hydrometallurgical refining process. You get metal salts, and then that goes back into then the cathode remanufacture. Now, essentially, these are the three steps that we need to establish in the UK. At the moment, we're on stage one, which is around here. And let me just get a laser pointer. So at the moment, we're installing this part. But what we really also need to install is this part as well. I think the cathode remanufacture will probably come with the battery manufacturing industry itself. But these two parts are certainly what we need to do, what we need to focus on. So a battery recycling process will go something like this. So this is a shred and sort process. So step one, essentially, initially you discharge a battery pack, then you dismantle it into smaller components or modules, and you shred those modules. Then the most hazardous part of the battery is the electrolyte. So you've got flammable and explosive materials in there. And I think Roger will talk a bit more about this later on. But you treat those in a number of different ways. So you can either treat them wet, so using a wet treatment process, or you can evaporate the material off and then condense it, and then you can sell it on again, or you can burn it off. But eventually once you do that, once you treat it, the shred then becomes safe. Not safe in the sense that you can expose people to it, but safe in the sense that it's not going to catch fire or it's not going to explode anymore. And then you do the initial screening or sieving step. So then that's where you get your first stage of black mass. Black mass is a powder that consists of anode and cathode material. After that, you can do a number of different separation steps before eventually you have to do another milling step where you're in the first screening stage here, you've still got a lot of the cathode and anode material stuck to the foils, the powder that you want. And so in the milling stage, you mill it so that you take more of the powder off. You then do another sieving step to get more of the black mass. And then finally, you got your density separation. You can separate the copper and aluminium. Now, this black mass contains about 90% of the value in the cells. And most of that value is in the lithium, the nickel, and the cobalt. And then there's a bit more value in the copper as well. But those four elements contain, I would say, 95+% of the value in lithium-ion batteries or end-of-life lithium-ion batteries. Now, there's a number of different companies that are aiming to put up a battery recycling process in the UK. So the one that has got there is RS Bruce through Sam Hague, and I think Sam's joined us today. So well done, Sam. There's another company called Reconi. They've got a process that recycles production scrap. And then there's a number of other companies that are in various stages of development. So you've got EMR, for example, although I don't know what their process, the tonnage is. I think they're going for a pilot scale first, and then they're going for a larger scale, which is the right way to go. But there's a lot of companies that are looking to set up in the UK, and I'm sure there's many more than this. These are just the ones that I've personally interacted with. So after you get the black mass, then the next step is the leaching step. So you leach it into acid. It's known as the hydrometallurgical recovery. So the first step is you leach it in acid. So you put the black mass into acid, and then the metals all dissolve into acid. The next step is then you remove the impurities. So things like the copper, the aluminium, the iron, and whatever else there may be in there. You remove those. Then traditionally, the next step is you then selectively extract one of these metals from the acid. So you add a solvent to it. The solvent selectively extracts the nickel, for example. And then the next step is you then transfer that nickel from the solvent back into an acid, and then you precipitate it out. Now, of course, it's not that easy because every time you, for example, you're taking the nickel out, you might take the cobalt out or the manganese out because they're very similar metals. So you have to do a number of different extraction steps before you can get the purity required. So actually what people have done is they've begun to go to newer approaches. So they're saying because we're recycling it back into batteries, there's no point separating all these metals into their individual components. Once you take the impurities out, you can get a mixed metal hydroxide. So you can then get a mixed hydroxide precipitate, and then that can go straight back into a battery. Of course, the problem with this is chemistry changes over time. So your process has to be flexible enough to deal with that. But this can seriously reduce the size of the plant that you require, and also the capital investment that you need as well. This chart just shows the worldwide lithium-ion battery recycling capacity. You can see that China has by far the most. We are currently less than 1,000 tons a year, but hopefully we'll soon be, when the processes come online, we'll catch up to our European competitors, certainly. So when we talk about battery recycling, there's two types of feedstock. So there's end-of-life vehicles, and there's production scrap from production facilities as well. So if we look at the production scrap, you've got anode scrap, cathode scrap. You've got cells that are partially made. So these could be the stacks or the partially completed cells. And then you've also got cells, modules, and you've got packs that fail quality control. Now, all of these will require recycling as well. What we need to do, however, is we need to make sure that we recycle them in the most efficient manner. And in fact, the scrap from the production facilities is likely to make up most of the feed until we get into the 2030s, when we will start to have some real end-of-life material coming in. So how much manufacturing scrap is there going to be? Well, if we assume that each gigafactory will be 20 gigawatt hours, 1 gigawatt hour is around 3,300 tons of cells. So 20 gigawatt hours is around 67,000 tons of cells. And if 10% waste is produced, then by 2035, we'll have something like 40,000 tons of waste just from production scrap. And of course, there'll also be quite a lot of end-of-life packs as well. So according to the SNMT, this is what they're hoping that the vehicle sales are going to be like in the UK. And then if we combine that with the age distribution of end-of-life vehicles, then we can get a sort of a rough idea of how much packs are going to be coming to the end of life by when. You can see that, yeah, we're going to have quite a lot of recycling, or we'll need quite a lot of recycling capability by 2030, something like 150,000 tons a year worth of recycling capacity. So how do we go from where we are today, which is less than 1,000 tons per year, to where we need to be in 2035, which is around 180,000 tons a year, and that includes the end of life and production scrap. So that's the big question. And the other question is, should we mirror the EU, or should we develop our own regulations? Now, I've heard some from the industry saying that actually, you know, we need to go to lower standards than the EU to encourage investment in the UK. But I don't think we should do that because, well, firstly, because we export our vehicles to the EU. And so if you have lower standards than them, they may not accept those vehicles. For example, if they require 4% lithium in those cells and we can only provide 2%, then they may not accept them. Of course, and the other question is, you know, should we have standards that are higher than the EU? Personally, I think we should mirror them because I think the EU standards are, they're quite balanced, and getting higher standards than what the EU has may not be possible given that some of the material within the batteries is really difficult to recycle. Then, of course, you've got the health and safety. Now, I think this is where we can lead in the UK. Roger, again, will speak more about this, but lithium-ion battery recycling is an extremely hazardous activity. You've got flammable, explosive, toxic, carcinogenic material in there. And lithium-ion battery recycling facilities will come under the COMA regulations. Now, the UK can be a leader in this field because what we've noticed is that a lot of the companies that are selling recycling plants, they're using standard recycling technology, and actually that's not fit for purpose. You know, this material is a lot more hazardous than people think it is. And so we can actually take a lead on this and become a leader in the field. And this is just a SWOT analysis with respect to battery recycling for the UK. So we've got a significant number of strengths. So for example, we're one of the largest, or we've got some of the most comprehensive experience in shredding and material sorting in the whole of Europe. I think we were the largest vehicle shredder in Europe. We've got excellent academic institutions. We've got private public funding mechanisms, which, for example, funded the Recovers project. We've got companies that have got good knowledge in hydrometallurgical recycling or refining. We're also an island nation as well, which means that the material that we produce here will be recycled here because it's very difficult or very expensive to ship it abroad. We're also one of the largest vehicle markets in Europe. And of course, there's no legacy industry here. So the rest of Europe have got, for example, pyrometallurgical recycling facilities, which they can't, multi-billion pound or multi-billion euro industries that they don't really want to, let them go to waste, basically. So they're kind of stuck with what they're able to do with them because obviously they're not as efficient, whereas we can go on a different path and get much more efficient recycling industry. Our weaknesses are, of course, at the moment, we've got no battery manufacturing industry or a very small one. We're also quite late to the game as well. So some of the other countries, they started this battery recycling more than 10 years ago. We haven't got much of a battery materials refining industry. Of course, with Brexit, it's also quite difficult to recruit talent at the moment. And there is a lack of health and safety expertise in the recycling industry as well. Many opportunities. So, for example, we can transfer best technology from abroad. We can develop our own innovative solutions, like what we're doing at WMG. We can build up an integrated industry. So, for example, again, Recovers is a very good example of this, but the public-private fundings enable us to build knowledge that would otherwise not be possible. We can develop our own standards if we want to. And of course, there are a lot of new OEMs that are setting up in the UK with the threats. So there could be a lack of funding for innovation, or at least it doesn't match the ones that is the funding that's found in other countries. The EU is seen as a better place to put battery manufacturing facilities. Unfortunately, that's the case at the moment. Political will, so we're turning over prime ministers quite fast at the moment. So from one to the other, we need to be stable. And of course, the other threat is that OEMs are leaving the UK, although hopefully they'll get replaced by new ones. So we need to have a very clear vision for 2035. Now, my vision is for 2035 is as such. So by 2035, the UK battery recycling industry should be able to achieve the following: provide at least 10% of the UK's metal needs through direct recycling of manufacturing scrap. So manufacturing scrap is stuff that can be directly recycled, because if it's sorted at the site of production, if it's separated from everything else, then it's a pure material stream that doesn't need to go all the way through a hydrometallurgical refining step. It just needs to basically be exfoliated and then put back onto a new foil. Shred and sort technology to give a minimum of 70% recycling efficiency for end-of-life batteries. Modular hydrometallurgical plants in operation producing 99.99 pure metal hydroxides. Flexible processes accounting for changes in chemistry. So for example, if you've got NMC N11 chemistry, and in 2035, the preferred chemistry is NCA, the nickel cobalt aluminium, similar to the one you find in Tesla, then the process should be able to account for that change and produce such material. The lithium iron phosphate, at the moment, nobody wants to touch these because they don't have any value. But the lithium iron phosphate technology, we need to develop that in order to A, meet our recycling obligations, but B, also because we're going to have thousands and thousands of tons of lithium iron phosphate batteries that nobody will recycle. And then we also need to develop supply chains for the recycling of non-metallic components as well. So at the moment, everybody is focusing on the metals, but of course, the rest of the components within the batteries also need to be recycled, particularly the graphite. There is, of course, a massive role for public-private partnerships. They're vital. Recovers is one such project, but I think I'll leave that to Roger to talk a bit more about that. But the Recovers project was designed to install the shredding and sorting capability in the UK and develop the safe handling procedures and safe shredding procedures. The next step is now to do a pilot scale hydrometallurgical refining process. The government's really interested in funding something like that. So if there is someone on the line that's interested in that, then please do get in touch. And then, of course, a cathode remanufacturing process as well. And just to finish off, so what are we doing here at WMG in terms of battery recycling? Well, we've got a number of different projects ongoing. So we're looking at battery diagnosis. So currently, when a battery reaches the end of life, the state of the art is to find out what state of health it's in. It's charged and then discharged, and that can take about 8 hours. And we're looking at a process that will do it in about 2 or 3 minutes, and will do it at an accuracy of about 98%. Also looking at battery discharge as well, but not discharging any old batteries. We're looking at discharging batteries that are, really have come from the end of life. So we've received some batteries that were in really bad shape. Some of the terminals were, almost completely corroded, but we managed to discharge them and then safely shred them. We're also looking at battery shredding as well, or at least having our own shredder on site, because essentially what we want to be able to shred the batteries that we produce at WMG and then get the material back out to then recycle it into new cells. We're looking at electrolyte drying and recovery. So the electrolyte treatment step is the most hazardous step, or at least the one that is rate controlling, because it's quite a slow process. And so we're looking at speeding that up. We're looking at lithium iron phosphate recycling. So I think we've come up with a method, and we're going to try it next week, that potentially could really change the way lithium iron phosphate batteries are recycled. At the moment, they're not recycled at all. Or if they do recycle them, they just strip the lithium off. But we're looking at a process that will upcycle lithium LFP batteries. We've already developed a lithium recovery process, which we've applied for a patent, so we can recover around 95–96% of the lithium at 99.9%, 99.7, 99.8% purity. We're looking to scale that up as well. We're also developing hydrometallurgical recovery processes using deep-eutectic solvents or conventional acids. And again, we've got some really promising results in that area, looking at lithium purification. So the lithium that we recover here, we can purify to 99.9%. We're also we've started a material remanufacture process, which we will then use the cathodes that we remanufacture in coin cells and then test them to see how they perform against material from virgin sources. Thank you very much. That was the end of my presentation.
Okay, and thank you very much, Anwar. I think we'll leave questions till the end until we've got the other two talks there. Thank you. But for those of you who don't understand, haven't followed this before, that was a really great introduction, and I do recommend his report, which is, I'm sure, downloadable from the WMG website. Next is Sarah. There she is. I'm just looking at the screen. Sarah, it is your turn. Please share your screen and give your presentation.
Brilliant, thank you. Just to double check, is my screen coming through okay?
Very, very clearly, yes.
Brilliant, thank you very much. Hi everyone, I'm Sarah Colbourn from Benchmark Mineral Intelligence. I'm not sure if you're familiar with us, but we cover and we collect data and publish data for the whole lithium-ion battery supply chain, from the upstream mining of the sort of key battery materials through to looking at sort of cell capacity and demand, and most recently covering the recycling space. So that's why I'm here today talking to that. So to start here, I thought it would just be sort of useful to kind of look at where we are with the demand for lithium-ion batteries. So this is sort of a global overview of the forecast of the growth and demand that we see across this decade. So you can see here that the majority of this demand will be coming from transport applications, sort of in response to global commitments to phasing out ICE vehicles and with the widespread adoption of electric vehicles. So between 2022 and 2030 alone, battery demand for transport applications, we're forecasting to grow by over 400%, which kind of speaks to the volume of demand. And with that, of course, the increase in the need for the raw materials for batteries, and then of course the actual battery grade materials too. And so with that, we can see a role for recycling. First of all, these are kind of a series of opportunities and sort of drivers for recycling. Firstly, with that kind of supply in mind, we are sort of forecasting across all the battery materials long-term, looking at sort of deficits. And with that, as recycling can sort of come into its own and build out capacity, we expect that that can sort of help to alleviate some of the shortfalls in supply. Sort of as well as that, given that, you know, certain regions have a stronghold on the upstream extraction and processing, for example, looking at cobalt, over 70% of the world's cobalt is mined in the DRC today and processed in China. As Anwar showed on there, with lithium, the majority is extracted either in South America or Australia and ultimately processed in China, and similar stories for the rest of the battery materials. So the opportunity with recycling is sort of opening up the scope for countries to sort of contribute to new domestic supplies via recycling. From a circularity and sustainability point of view, recycling this material, whether it be that scrap from gigafactories or those end-of-life batteries, recycling those, collecting them, recycling them is really fundamental to closing the loop on the battery supply chain and transitioning to a circular economy. And then lastly, just another sort of thought that's really, really linked to recycling and circularity and sustainability more broadly is that as we are able to sort of reduce reliance solely on sort of the extraction and processing of virgin materials, that in turn will reduce some of the ESG risk, that environmental, social and governance risk that tends to be associated with the upstream of the battery supply chain. But of course, to sort of talk about recycling and sort of the materials that ultimately can be recovered from recycling, we need to understand what material is going to be available and when for recycling. So in the short term, as Anwar sort of touched on, we're forecasting that in 2022, over 70% of the global total scrap pool will be composed of that processed scrap. So that they're like losses coming out of gigafactories, which are inevitable throughout the course of cell manufacturing. as a new plant comes online or a new line is introduced at a cell facility, those loss rates can be really, really high in sort of the first year, 2 years, and that during that ramp up period. Ultimately, those loss rates will reduce sort of as time goes on and as lines mature. However, there always will be losses there. And therefore, with that, there will always be material that will be available for recycling. So in the short term, sort of for the next decade or so, this is the kind of material that will dominate the feedstock for recycling. And as this material is absolutely linked to cell supply, the majority of this material lies in China and East Asia, where a lot of that cell capacity lies. Therefore, there are sort of relatively limited supplies of this kind of material in Europe and North America at the moment. However, in the early to mid 2030s, we're forecasting that there will be an inflection point whereby end-of-life batteries, so those that are sort of in the market being used, whether it's in a mobile phone or a power tool or indeed an electric vehicle, they will ultimately reach their end of life and be available for recycling. And so long term, it will be these batteries that will sort of take up the majority of that total scrap pool. And so with that, there are both challenges and opportunities, of course. From an opportunity and point of view, as these end-of-life batteries are a product of demand, they will be sort of more widely distributed across the world. So they'll be increasingly accessible to recyclers. Of course, with that, there are challenges from a logistic point of view. The collection of these batteries and indeed the transportation of them is something that kind of needs a development both from the industry and also from policy. There have been sort of movements across the world in different sort of jurisdictions to introduce extended producer responsibility rules, which sort of determine who ultimately will be responsible for collecting these batteries and ensuring that they are recycled. Just to sort of give an overview of the sort of magnitude of material that we are expecting to sort of become available for recycling between 2022 and 2040, we're forecasting over 20% compound annual growth rate in this total scrap pool, which kind of indicates the size of the volume of material that will be available for recycling and will of course need recycling also. Sort of delving a little bit deeper into that end-of-life scrap pool, I think, of course, it's really important to understand what kind of material is going to be in that scrap pool. So today and sort of for the next few years, a significant portion of this scrap pool of these spent batteries will be LCO batteries. And that's kind of unsurprising given that at the moment, the majority of batteries that have reached their end of life and are therefore available for recycling are portable batteries rather than electric vehicles or energy storage systems. And therefore cobalt-rich chemistries such as LCO are favourable for those kinds of applications. As we make our way out across this decade and then sort of 2030s beyond, we're expecting more NCM chemistries to sort of be in that scrap pool, particularly nickel-rich chemistries due to them being desirable for transport applications. And then, as Anwar touched on as well, we are expecting a growing supply of LFP batteries in that future end-of-life pool due to the renaissance that LFP is sort of going through at the moment as a cathode chemistry. Of course, it's really perhaps quite obvious, but important to bear in mind that trends that we're seeing today in chemistries for batteries, of course, will appear in the future end-of-life pool due to the lag of batteries actually in use and how long they might be in an application for, and indeed perhaps even in a secondary application too. And with that, sort of looking at what is sort of going to be in that end-of-life pool, it brings us on to the technology. Historically, pyrometallurgical technologies have been sort of most popular in the recycling space, and they're able to recover the nickel and the cobalt, but really not being able to recover that lithium. However, kind of on the back of that and sort of the awareness of the need for lithium and a series of other drivers, we're seeing more recyclers opting for hydrometallurgical technologies, and some development of direct recycling technologies, though that's sort of yet to be proven at a commercial scale. We sort of see a lot of activity at the policy side of things and sort of expect that to play a role in shaping the development and advancement of recycling technologies. If we look to the EU with the Batteries Directive, that like Anwar touched on, there will be recovery targets for lithium, nickel and cobalt, That's kind of what I'm focusing on here. So that surely is going to sort of push the industry forward in sort of promising higher recovery rates, particularly on the lithium front. And also it's worth bearing in mind here that attention from the industry and from government level as well very much has been on the recovery of cathode materials, with the kind of anode recovery and the graphite recovery largely being kind of sidelined at the moment, which is something to sort of bear in mind, I suppose, for the time being. Here, I thought it was just quite useful to kind of visualize the increasing role that we are expecting recycling to take in sort of helping to meet the demand for the entire industry. So here in each of these respective market balance charts for lithium, nickel and cobalt, the red line going up indicates the forecast demand for these materials. The yellow bar is that of mine supply or sort of traditional virgin material extraction and processing. And the blue bar indicates the growing role that recycling can play. So a few things to note here, I suppose. First of all, across each of these markets, we are expecting recycling to play, to sort of compose a higher proportion of total supply as we make our way out to 2040. That's due to a few reasons, really. I suppose, firstly, more recycling capacity coming online. Secondly, the sort of increased availability of feedstock for recycling. And of course, the expected sort of development in recycling technologies and sort of bettering recovery rates. The other thing to bear in mind is, of course, that we are still expecting mine supply, sort of that virgin material, to help sort of contribute the highest proportion to overall supply for the foreseeable at the moment. And of course, even with that, we still are sort of looking at deficits. So there's a lot of scope for recycling to play a role. And as more capacity is announced, of course, the sort of hope for recycling to help plug that gap in supply is sort of growing. And finally, I think it's just very important to acknowledge that there are a series of huge opportunities for recycling in the battery supply chain, but due to the sort of nascent nature of this market, there are a lot of challenges yet. So in the short term, sort of going back to that idea of process scrap being the main source of recycling and for the foreseeable, securing that feedstock for recyclers will be a challenge. But what we're seeing is a lot of partnerships between cell manufacturers and recyclers, sort of mutually beneficial, really, securing feedstock for recyclers and ultimately that source of secondary material for the cell manufacturers. In the sort of near, mid and long term, the logistics is something that needs to be thought about, as I mentioned, with the collection of batteries, determining who is ultimately responsible for collecting them and the transportation of these batteries too. And then on the technology front, I think there's a lot of work to be done, particularly on the lithium recovery, but also the anode recovery too, if we look beyond cathode materials. And then lastly, looking to the policy, which kind of will impact every area of this. As Anwar mentioned, Europe's sort of charging ahead with looking to mandate the minimum recycled contents in batteries from the end of this decade. And then if we look to North America, just for comparison, with the recent Inflation Reduction Act, they're including recycled materials in North America to be eligible for the EV tax credits. So we can kind of see different approaches to incentivizing developments in the recycling market, whether it be the carrot or stick approach. We're seeing a lot of activity there, but expecting policy to play more of a role as we see governments around the world starting to really recognize the need to recycle from a sort of circularity point of view, but also the big role it can play in helping to meet supply. And with that, that's the end of my presentation. So I'll hand back to you, David. Thank you.
Thank you very much, Sarah. And it's interesting, if you put Anwar's presentation and Sarah's together, you'll find there's a strong commercial driver. If we have nothing but battery electric vehicles on the road in 2040, and we're recycling at the sort of rate we anticipate, then a 1% increase in efficiency of recycling is worth a couple of £100 million in the UK alone. So no small task, Roger. Can you tell us how we're going to make money out of this very, very necessary process?
Afternoon all. Well, I'll give it a go on and at least sharing what we've learned so far in trying to do that. So yeah, can you?
Yeah, I can see it.
Can you see something saying recovers?
Yep, nice picture.
Great. Okay. So yeah, just going to talk about what we've learned so far in the Recovers partnership. I'll just explain the partnership and then a little bit about EMR, and then the key things we've learned in the course of our work together with our other partners on Recovers, and maybe there's lessons for other people too. Great introductions there, or explanations from Anwar and Sarah that very much set the scene for what we're doing now. So the aim of the Recovers partnership was a collaborative R&D project, which is partly funded by the government's Advanced Propulsion Centre and Innovate UK, is to see if we can build a fully commercially viable circular EV battery supply chain in the UK. And I've added on to that to do it safely, because that's one of the key learnings that we've had from this exercise. Just to explain the partners, we've brought together 3 of the UK's leading vehicle makers, BMW, Bentley and Jaguar Land Rover. We've also got some great academic and institutional partners. We've got UK BIC, Anwar and his group at Warwick, and then the Health and Safety Executive. And then EMR is the recycling partner. And then we've got Autocraft and Connected Energy, who are remanufacturing and reuse partners. Because if you want to create a circular supply chain for batteries, it's really important that you have reuse and remanufacturing as part of that, because they're the highest value outlets, much more valuable than just material recovery, which should be the last one on the list. So if we want to make that circular supply chain work, we've got to be able to pay the most we can for a vehicle at end of life. So if the battery can be reused or remanufactured, we need to do that. Just to explain the circular supply chain that we're aiming to set up here. At the top left, you've got an electric vehicle reaching end of life, coming into EMR's car recycling centres. There we'll depollute the vehicle, or people like EMR too, of course. Recover the metals and plastics like we do today. We recover plastics good enough to go back into new cars, and recover metals good enough to go back into new cars. The battery we'll take out, and we'll do what we call a triage process to work out whether it's suitable for reuse or recycling. If it's good for remanufacture, it'll go to someone like Autocraft. If it goes good for reuse in grid storage, it will go to someone like Connected Energy. If it's not good for that, then we'll go to the recycling centre, do that shredding process that Anwar was talking about, onto a refiner, as he was describing, then to the cathode manufacturers, usually a different company, into the gigafactory that makes the batteries, and back into the circular supply chain and back for reuse. And we've got HSE, UK BIC and WMG there at the bottom, just to remind ourselves that they're the people who are helping us with the thinking about how to do all this. The aim of the project overall is to get the end of life pack disposal costs for vehicle makers or the last owner to zero, so that we can still pay a positive value for a car at end of life like we do now. And I think that's very much a realistic expectation these days. And of course, we want to keep those resources in the UK and generate some new economic activity. Just a little bit about EMR, biggest metal recycler and plastics recycler in the UK, family owned. We invest our profits. Overall, we process 10 million tonnes a year of end-of-life products, 4 million of that in the UK, 4 million in the United States. We're a UK business, but we have a lot of operations in the US, and we do 2 million tonnes in Northern Europe as well. And we've got a clear plan to be net zero by, clear objective to be net zero by 2040, clear plan to getting most of the way there by 2030. We're not sure, like anyone else, exactly how we'll get all the way there by 2040, because those technologies are not there. But it's important to be net zero in your own operations if you're selling fundamentally net zero products. Just in terms of our position in end-of-life vehicles, we're biggest recycler in the UK of conventional internal combustion engine vehicles, 54 sites across the UK. And we're working hard on developing that technology. In fact, in the US, we have this operation called My Auto Store in Camden, New Jersey, which we're looking to replicate in one way or another in the UK quite soon. This is a disassembly line for vehicles. It looks like an assembly line running backwards. Got all manner of vehicles coming in, and then we're pulling parts off which we're selling all around the US doing the depollution, and then anything that's left goes into the shredder that is at the end of the line there. So we're looking to develop some of this sophisticated technology into the UK as well for conventional cars as a precursor to doing electric vehicles. So that's just a bit of background about us and the partnership we're in. What have we learned working with our partners about electric vehicle battery recycling? Well, firstly, internal combustion engine electric vehicles are really different. Pretty obvious, I suppose. On the outside, the electric and internal combustion engine versions of these vehicles are pretty much the same. But the ICE version, we can just take the wheels off, drain the fluids, remove the catalytic converter, and pretty much we chuck the rest into a shredder. It's chopped up into small pieces in about 15 seconds. And then we have large complex processes to separate all those different materials, the copper, the aluminium, the lead, all the other minor metals, and then the plastics go through a complex material recovery process, and we recover polyethylene, polypropylene, ABS, and polystyrene, good enough to go back into new vehicles and electric equipment. We've developed that over many years, and other companies like ours do the same thing. Electric vehicle, you can't do the same thing, because actually, once you've got the battery and the drive motor and the control unit and the wiring out, which are quite discrete components, then there's not very much left to shred. So there's nothing like the same sort of value from a metal recycler's point of view in shredding, and it would obviously be too dangerous. You can't shred batteries along with everything else. So we're going to very much more of a manual disassembly process for vehicles, and then just a final shred for the bit that's left. So it's a completely different value proposition to what we do today. And that's part of why we're developing these technologies like My Auto Store to take components off vehicles much more efficiently. The next thing, which Sarah alluded to, is although the sales of cars are going nuts, so the columns on this graph are the forecast sales of electrified vehicles in the UK, and the yellow line is the forecast sales of non-battery containing cars, down to pretty much zero by 2030. That translates into a very different picture for end-of-life vehicle arising. So the yellow line is the number of cars. Something like 2 million cars a year reach end of life in the UK. Not all of them go through the conventional recycling system, but most of them do. The growth in end-of-life ELVs is electric vehicles is offset quite a long way. If you look at 2030, there were still around about 100,000 a year we're forecasting, much less than the number placed on the market, and that's sort of emphasized by this graph here, which shows the blue line is the cars, electrified vehicles sold in the UK up to 2040, and the cars reaching end of life. So this huge 15-year lag roughly between those placed on the market and when they reach end of life, which means that there's not a desperate rush to put enormous capacity in. In fact, the problem is there's actually not enough supply for us to justify putting a lot of capacity in at this point. However, in absolute terms, the numbers of vehicles reaching end of life are quite a lot. So even 10,000 vehicles a year, or 1,000 a month, is a lot to learn how to handle at this point of the market. So that's an interesting challenge that we're juggling with. The next challenge is that the variety of batteries and chemistries that we're getting is incredible. 70 or 80% of the cars placed on the market, all cars placed on the market in the UK, come from outside of the UK. 70% of the vehicles made in the UK are exported. So there's an incredible range of new models of hybrid and full BEV cars coming into the UK, plus all the other things that we might want to recycle, like e-bikes and scooters and other smaller battery containing items. So that has implications for how we do the recycling, and we're learning a lot about that in this collaboration, working particularly with the health and safety executive. We've lots of training for our high voltage technicians on how to approach these very different batteries for which we have no data, carefully and developing almost a contradiction in terms, a standard operating procedure for unknown constructions of batteries. At the same time, we're building our database so that we learn as each new battery type we take in, we're learning how to handle that, how to dismantle it, what the value is likely to be, and building a whole portfolio of those dismantling procedures to learn how to do that. And actually, that's really quite a large chunk of the value that we're generating at the moment, because there is value in that knowledge of how much effort is needed for each battery type. We might be naive, and I think Anwar referred to that, may have been naive, but you know, when we started on this, we thought we could do recycling pretty much like we do recycling today with shredding and separating and so on. We'd seen people in Europe doing it pretty much like we do other things, but quite a few of them were covered in dust. And what we've learned is that those risks are much, much greater. It's partly through interacting with people like Anwar and other university groups, partly by working in close collaboration with Johnson and Matthey, who until recently were really big, developing a big play in hydrometallurgical recovery. They've now decided to move out of that, which is a shame for the UK, but we learned lots from them while we're doing it. And there really are a lot of risks that are we sort of aware of them, much greater than we expected. So the fire risks that I've listed there, the risk from dust explosions from the graphite, and the chemical safety of these materials. The threshold limit values, the exposure limits for these materials are much, much lower than we'd understood. They're carcinogenic. Some of the cathode materials are permanent sensitizers. And probably the biggest risk that we didn't understand was the capability of these fluorinated compounds to decompose from even 85 degrees, certainly 100 degrees centigrade plus, and liberating hydrogen fluoride in quite low concentrations, but still very damaging and toxic. So what we're doing about that is that we're putting in much higher containment process equipment and material transfer systems than we originally anticipated. We're segregating the processing cells for our equipment and putting all kinds of exposure monitoring and emergency kits in place for our people. Another big learning that, again, Sarah and Anwar referred to and is not regularly spoken about at these sort of meetings is that lithium iron phosphate's coming. You know, we're not making many cars with that technology in the UK because we're producing high performance vehicles in the UK, luxury vehicles, but 80% of the vehicles, as I say, coming into the UK are mass market vehicles from outside. And a lot of those are getting into LFP chemistry much faster than we expected, and therefore will be reaching end of life in the UK. And what we're learning that for these vehicles, and even for non-LFP vehicles, if you want competitive advantage and to be able to give a positive value for the battery at end of life, you've got to learn how to generate value from graphite and electrolytes. And we don't see a lot of excitement in the research community about that, but we are encouraging. We're putting several grant applications with a couple of different university departments, and we're trying to encourage others to get engaged, working out how to get battery grade graphite back from end-of-life batteries, and also see if we can recover value from the electrolytes. Particular challenges about that on recovering graphite. You know, do we do the primary shredding wet or dry? How do we regenerate the surface properties? And that may also affect whether we recover lithium first or last, and how we would recover clean electrolyte materials. So there's some really quite complex interactions there that we all feel everyone should be putting more effort into than they currently are. So conclusions overall, yeah, different recycling techniques needed. We've got to be prepared for big pack volumes, but we've got to learn how to cope commercially with small volumes today, which is quite a challenge. If there was massive volume coming today, it would be much easier to justify huge investment. We've got to handle this incredible variety of pack types. The safety risks are much higher than we, and I think others realised, and I think that's a word of caution to others getting into this game in the UK and Europe. And cobalt and nickel, we don't think is enough to be competitive, we've got to be able to get graphite and electrolytes and other materials back from these batteries. So I hope that is helpful, and look forward to the discussion.
Actually, thank you very much, Roger. And I'm guessing all the chemists on the call were going, hydrogen fluoride, because they recognize that problem. Okay, are there any questions at the moment before we go into the discussion session? Any particular questions? Now let's go and talk about what we've learned. Welcome back, everybody. So the idea now is to just have a quick feedback from the three groups about what turned up in the conversation. And I'm going to go with Andy first because he's done this before so many times. He's a skilled rapporteur.
Thanks, David, and thanks to what was quite an intimate, a small group, but we had some really good conversations, I think. So we started off talking about who's going to own the metal and how is this overall supply chain going to work when you look at the increasingly protectionist and deglobalized world that we're potentially moving into. So when you've not got the opportunity for closed loop within an island, within a country, whatever, you know, within a given ecosystem, what challenges would that present? And you know, and then we thought about going on to world poverty after trying to solve that one for a bit. So so we moved on, but sort of logged that as obviously quite an important consideration, and also looked at the potential for unintended consequences in some areas of policy, particularly when you are mandating certain proportions of materials that have got to go into a given product going forward, which is what the EU is doing. And I think on these calls before, you know, we talked a little bit about, well, if it needs to be battery grade, then you're automatically raising the bar there fairly significantly to do that. And then we talked about the importance of LFP recycling and the fact that, you know, that's not really done today effectively. So some big opportunities there for those working in that field, and not just on the car side, because a lot of the trucks that have batteries in going forward will be using LFP rather than the high nickel levels and things like that. And then a final really useful conversation between Anwar and Tony around APC, ATF, best funding models if you want to put something fairly large and with hydrometallurgy on the ground in the UK. So, you know, some good connections made there, I felt.
Excellent. Okay, and Tom.
And really strong group of people on the call, touched on many of the same topics, I think, that we touched on in the talks and also I think in Andy's group. One, obviously, was the nature of the market. It's one that we're all predicting, I think, inevitably has to rapidly grow with the market, but it's that process of getting pioneering operations going and then growing with scale over a period of time. We touched on safety as being a key part of that. Obviously, you're dealing with what are dangerous, quite energetic materials, and there's a lot of work that needs to be done up front in considering the hazards, but you may still need to go back and work out that you need to tweak and adjust things going forward. And materials, how important it is, and how and if you can do that was something we also touched upon.
Okay, so for my group, again, great thing. Brilliant question from Emma. Obviously, Brent didn't ask the same question in his screen about, what does this mean for sodium batteries? Because we need to go back and address that, because we've had the session where Jerry came and evangelized about sodium batteries, but we weren't thinking about that. Really good point. I think Roger made the point about disassembly, and we had a question about why people weren't designed. Somebody always knows in these things that old Teslas are useless, and I feel embarrassed about that. But I do think Andy Abbott talked in episode 3 about the need to design the batteries to be taken to pieces more easily and such. I mean, you know, Roger's point that everybody knows how to take apart a conventional internal combustion car and get it into the right bits. It's much more complicated with batteries. And then finally, we had an interesting conversation because Mick Adams' company does hydrometallurgy. So we sort of got to the source of the types of batteries is changing over time, and I wonder how flexible hydrometallurgy processes are or can be to accommodate the evolution away from high value metals to lower value materials in general. And then everybody was struck by the metals aren't enough, we have to recycle as much as possible. I mean, it's the great thing about a battery electric vehicle is it's roughly the same lump of chemicals at end of life as it is at the beginning, sort of thing. So you can do something, but we put them in very complicated structures, and how you separate them out when they've been intimately mixed is a really challenging thing. So I think the take is from all of us that this is really important to get right. There's still lots of fundamental science. There's a lot of process chemistry and engineering that needs to be done, and then that all has to be taken through and made commercially viable. And Roger spoke quite eloquently on that, and I do see Josh is on from BIFA, so they're a challenge for you, Josh, as well. Just about at the end of the thing, anybody any questions or points they wish to make? If you have any ideas for episode 9, as it were, please write to Callum or I. Andy and Robin and I will meet together fairly soon to decide what the potential topics are for episode 9, and then hope to see you again at that. So goodbye, thank you very much, and have a good week.
Thanks all.
Bye.
Bye.
Okay, thank you. Bye.